What is a covalent bond? Imagine, for example, a carbon atom with a certain radius, and its valence electron has a bonding energy equal to the ionization energy. If another carbon atom appears nearby, under suitable conditions, both of them will desire to bond with their valence electrons. However, for electromagnetic forces to remain in dynamic equilibrium, the atoms must move away from the close distance of their atomic radii and reach a distance that satisfies the equilibrium of electromagnetic forces that hold this bond together. At this distance, their bond has an energy lower than the combined energy of the original atoms in close contact. The difference between the bond energy and the sum of the bond energies of the original atoms is called the bond energy. The greater the energy released during bond formation, the higher its value, the more tightly the atoms are bound together. A covalent bond is a force interaction between atoms of either the same or different elements. It is characterized by the sharing of one or more pairs of electrons between two elements, bond length and bond energy. In the following presentation, we will show how to calculate the magnitude of forces, bond length, and bond energy of a covalent bond according to the ring theory. To explain the principle of a covalent bond according to the ring theory, we need to start with the magnetic moments of elementary particles. Currently, the magnetic moments of the proton, neutron, and electron are experimentally demonstrated and very precisely measured. What does the magnetic moment tell us about elementary particles? From physics, we know that the magnetic moment of a planar current loop with an area S, carrying a constant electric current I, is equal to the product of the current and the area and is oriented in the direction of the surface normal according to Ampere's right-hand rule. Therefore, if elementary particles like the proton, neutron, and electron have experimentally measured magnetic moments, we can hypothesize that all these elementary particles have a similar structure, resembling a current loop, where the current is created by the movement of charge around the ring or toroid. In the case of the proton and neutron, the ring theory works with the hypothesis that three quark particles always define a plane. If there is an exchange of energy between these particles, for example, the movement of charges in one direction, we can associate this process with an electric current in a closed current loop and apply the known laws of electromagnetism to it. To define the magnetic moment, we need to know the radius of these particles. However, only the proton's radius has been experimentally measured. We can assume that the neutron's radius is very close to the proton's. The radius of the binding electron of a particular element can be calculated using the wavelength of the photon from its term, according to the ring theory. Regarding the magnetic moment of the electron, among the physical constants of particles, we find the so-called Bohr magneton. It represents the orbital magnetic moment of the electron of a hydrogen atom and is derived from the orbital angular momentum of Bohr's model of a hydrogen atom with a radius of 5·29 × 10⁻¹1 meters. However, in 1913, when Danish physicist Niels Bohr derived this relationship for the orbital magnetic moment, neither the proton nor the magnetic moment of the proton nor the intrinsic magnetic moment of the electron was known. It was experimentally measured only in 1923. Interestingly, its magnitude is almost identical to the orbital magnetic moment of Bohr's magneton. The magnetic moment of the proton was experimentally measured much later, in 1952. If, in the case of Bohr's model of a hydrogen atom, we take into account the interactions of magnetic moments between the proton and the electron, the bond length between them will be larger in the case of parallel vectors, and smaller in the case of anti-parallel vectors, and the mentioned Bohr radius would not be a physical constant. Even in 1925, when Schrödinger's equation was established, the magnetic moment of the proton was not yet known. Therefore, this equation does not take into account the magnetic field of elementary particles, their magnetic energy, or the magnetic interaction of elementary particles, which is equally strong as electrostatic interaction. Most quantum mechanical calculations include only electrostatic interactions between electrons and the nucleus and between electrons themselves. However, the magnetic energy presented by the magnetic moments of elementary particles has been overlooked. Can this theory be correct without the existence of magnetic moments of elementary particles? However, if we depart from Bohr's model of a hydrogen atom with a freely moving point-like electron around a positive proton, and replace it with the ring model of the proton and replace the point-like electron with the electron model with a multi-level ring structure according to the ring theory, where electric charge moves around the ring, we will see significant changes in the relationships between the proton and the electron. In Bohr's model, As the distance between the proton and the electron decreases, the magnitude of the electrostatic force increases exponentially inversely with the distance, approaching infinity. On the other hand, in the ring model, as the distance between the proton and the electron decreases on the common axis, the electrostatic force in the axis of the rings, after the initial increase, decreases to zero. The magnitude of the electrostatic force is influenced by the radius of the electron. If we associate the proton with a current loop, we can use the Biot-Savart law to determine the magnitude of the magnetic induction at a point P located outside the axis of the ring. If this point is located on the ring model of the electron, the non-uniform magnetic field of the proton will act on the current loop of the electron with a force. The magnitude of this magnetic force in the axis of both rings can be expressed using the modified Biot-Savart law. If the vectors of their magnetic moments are antiparallel, the force between them will be repulsive. Therefore, if we use the physical laws for attractive electrostatic and repulsive magnetic force between ring models of the proton and the electron, we can create a model of a hydrogen atom based on the balance of electromagnetic forces. Hydrogen atoms are atypical, but we can demonstrate calculations of electromagnetic forces, electron-proton distance, and bond energy, which we will need for the calculation of covalent bonds. The ring theory presents a model of a hydrogen atom as a system of a ring-shaped proton and a ring-shaped electron on a common axis. The vectors of their magnetic moments are antiparallel. Proton and electron are held on a common axis at a distance d in dynamic equilibrium by the attractive electric force and the repulsive magnetic force. We calculate the electric force in the axis of the rings using Coulomb's law and the magnetic force using Biot-Savart's law. In these equations, we express the hypotenuse and the sine and cosine functions using the values of and d. Since the motion of the electron's charge in the ring structure is not linked to the rotation of its structure, there is no need to calculate kinetic energy or the mass of the electron. To calculate these forces, we need to know the radius of the electron, ρ, and the electron's current, i.e. The size of the radius of the electron model of the hydrogen atom at the basic energy level is based on the terms of individual series of spectral lines. We calculate the electron radius of a hydrogen atom at the base level according to the formula term times constant alpha divided by 2 squared times 2 pi times n squared, where n is the energy level of the individual series of spectral lines. After substituting the values, we get the calculated size of the radius of the hydrogen electron model at the first energy level of 2.65 times 10 to the minus 11th of a meter. The magnitude of the radius of the electron calculated in this way corresponds to the experimentally measured value of the radius of the hydrogen atom. We can also calculate the value of the electron current, which we need to calculate the magnetic force. From the modified equations for the equilibrium state between electric and magnetic forces, we get the equation to calculate the distance d on the common axis. After substituting constants and previously calculated values, we obtain the value of the distance between the proton and the electron on the ground state energy level of the hydrogen atom, which is 2.34 times 10 to the minus 11 meters. This value corresponds to the experimentally measured values of the size of a hydrogen atom. According to the ring theory, the model of the hydrogen atom in the ground state is formed by a ring structure of proton and electron on a common axis, at a distance of dynamic balance of electrostatic and magnetic forces. From the equations for calculating electromagnetic forces, we can express the equations for calculating electric and magnetic energy on the x-axis. From the graphs of these equations, it is evident that at the equilibrium distance, there is no balance between the energies, but the magnetic energy has a higher value than the electric energy. The difference between the electric field energy and the magnetic field energy on the x-axis at the equilibrium point indicates the energy required to detach the proton from the electron. This value is called the bond energy. In the case of a hydrogen atom on the ground state energy level, the bond energy equals the ionization energy. Because we have calculated the necessary values for atoms involved in bonding, we can understand how a covalent bond works according to the ring theory. For a covalent bond to form, it is necessary for the vectors of the shared electron's magnetic moments to be parallel. In such a case, The magnetic field created by the rotation of charges will bind both electron rings on a common axis. This condition will allow both electrons to interact with the same electric and magnetic force with both one and the other proton of the nucleus of both bound atoms. Since the charges of the electron rings are on opposite sides of the rings, they do not exert a repulsive electrostatic force on each other in the axis of the rings. The two bonded atoms must find a bond length that ensures a dynamic balance of the attractive electrostatic and repulsive magnetic forces between the electrons and protons, and the repulsive electrostatic force between the protons of the two atoms. To illustrate the calculations of bond length and bond energy, we will consider the bond between carbon atoms. A carbon atom can bond with another carbon atom through its 2p electrons with opposite magnetic moment vectors and one s electron, and combinations thereof. For electrons of type 2p, we can calculate the radius of the 2p electron, its distance from the nucleus of the atom, and its binding energy to the proton according to the previous images. We can perform the same calculations for an electron of type 2s. We can determine its radius, bond length, and binding energy. From the calculated values, we see that the type 2s electron is located closer to the nucleus of the atom and has a higher binding energy than the type 2p electron. The bond between two carbon atoms can be realized by a pair of 2p electrons in single bonds, or by a pair of 2s electrons in multiple bonds. In the bonds of aromatic molecules or conjugated bonds, the bond can be formed by one electron of 2p type and one electron of 2s type. The difference between a single bond with electrons of the same type and electrons of different types is reflected not only in different bond lengths but also in different bond energies. However, in chemistry textbooks, it is often stated that bond length cannot be calculated but can only be measured experimentally. An example of a model of a simple homonuclear bond between carbon atoms. The bond energy between two carbon atoms is calculated as the difference between the sum of the energies of two individual carbon atoms and the energy of their bond. First, based on the equilibrium state of forces, we calculate the bond length and then calculate the bond energy between the carbon atoms. The bond energy released during the formation of the bond is equal to the difference between the energies of the individual carbon atoms and the energy of their bond, which is known as the bond energy. The calculated bond energy corresponds to the experimentally measured value. Similar calculation procedures can be used for calculating double or triple bonds between carbon atoms. An example of a model of a double bond between carbon atoms. An example of a model of a triple bond between carbon atoms. This text and the following table show that using the ring structure model of elementary particles, the structure of atomic nuclei, and molecular models according to the ring theory, we can, based on the basic physical laws and properties of electromagnetic fields, deterministically and relatively simply determine atomic radii and their ionization energy, the distance between atoms and their bond energy, not only in covalent homonuclear bonds. For more information and detailed calculations, visit the website www.ringtheory.eu. Thank you for watching the presentation with an open mind.